Swayam Prabha. Digital India. Educated India.
So, we are discussing this pH diagrams, discussing P versus H. Told you come along an isotherm at a particular pressure, you have this equation mu alpha is equal to mu beta, this is phase equilibrium. But we have also seen this is the same as G alpha is equal to G beta. For pure substances, the chemical potential is simply the free energy, Gibbs free energy per mole. So, this can be written as we have said at phase equilibrium T alpha is equal to T beta is equal to T, P alpha is equal to P beta is equal to P. Pressures are the same because you have mechanical equilibrium and thermal equilibrium, and so this gives you chemical equilibrium. So, thermodynamic equilibrium has three components: thermal, mechanical and chemical equilibrium. So, you have S alpha dt So, you have your Clausius-Clapeyron equation that tells you that dP by dt is equal to delta S by delta B, and this implies that delta H is equal to T delta S. So, this is delta H by T delta B. This is your Clausius-Clapeyron equation which you are quite familiar with. But the idea is that the pressure becomes related to the temperature by this equation at some, if you take a substance and lower the pressure at some temperature below the critical temperature, this is T is equal to Tc. So, below Tc you take any isotherm, if you keep lowering the pressure and move along the isotherm you reach a pressure at which two phases form. Then here if you decrease the pressure further you have the gas phase here, the vapor phase here. So, we have in this region of course we have all the isentropic lines, this is S is equal to constant, this is V is equal to constant and so on. You can read any of the values. It takes two coordinates to fix the position of a state. For example, here any H and P will fix the position, then you can do it in terms of any two variables. If you fix the temperature and the pressure, this point is fixed. If you fix the temperature and enthalpy, this point is again fixed. So, any two variables will specify the state of the system. Inside this region, this is say liquid plus vapor typically. I have given you the chart for methane, this is plotted from experimental data. Here also you need two variables because you have one variable temperature which will determine the pressure and therefore all the values at saturation. Similarly at the vapor end, but in between how much of vapor and how much of liquid is present is specified by an extensive variable. There is a variable here, it is usually denoted by x, is equal to fraction of vapor. So two variables are required to specify the state of the system, any two will do. Now if you want to calculate work, for example, you want to know what is the maximum work. Typically, for example, you compress a fluid, you compress it, as I said, adiabatically, simply because compression is usually done by, it can be done by a rotary device or a reciprocating device, and the compression time is very small. It is so small that the amount of heat transferred to the fluid is negligible. If you take a rotary device, for example, typically it rotates at 1000 rpm or 1200 rpm for convenience. That means per second you have 20 rotations. So in 20 times a second it gets compressed. So 1/20th of a second, how much heat can be transferred to the fluid. So effectively it is adiabatic. If it is adiabatic, you know that the entire work done is simply the enthalpy change. So if you take an S is equal to constant line, adiabatic reversible case, then if you are compressing from some pressure to some other pressure, from this point, let us say, do not need to be on the saturation line, does not matter, I seem to have drawn it here. So this point is A, I take vapor at this pressure and compress it from A to B. The amount of minimum work that I have to do is the enthalpy along the isentropic line. So this will represent, for example, the minimum work per unit mass or per mole, depending on what the plot is. So essentially calculating minimum work simply means on this chart identifying position A and position B, the initial state and the final state. If it is isothermal, you will go along an isotherm and calculate delta G. If it is adiabatic, if it is a closed system, then you will calculate delta U, and if it is finally a closed isothermal system, you will calculate delta A. Let me do an example. Yeah. This is adiabatic case. Now, a device that people carry on the back for underwater operations has a huge tank, actually it has a small tank and a huge tank, two tanks. Then you have a valve here, you have a expansion device, this is put into this. Okay, I have tank 1 and tank 2. This contains, at t is equal to 0, this contains initially compressed air at say P0 bar. You know what the units on this chart are. The old units are all, oh they have made it SI units, megapascals, does not matter. Some pressure, this is initially evacuated. What you do is at t is equal to 0, you open a valve, allow this air to expand here into this. You could let it out in the open if the pressure is sufficiently low, but for example for deep sea activity, if you are 10 meters below sea level, you are talking 10 bar already, the pressure there. So if this is filled to 10 bar, the gas will not leave at all if you open the valve. So you have to have another container. Secondly, there are environmental considerations, whether the gas that you put in, if it is air it is okay, if you are taking some other gas for operations, you do not want to let it out into the sea. So what you do is pass it through an expansion engine, this engine will rotate, this will give you work, shaft work. So as the gas expands from one tank to the other, it turns a shaft which will do work for you. You may do minor repairs, you may take the hull of a ship and break up the crusts that are formed at some places and so on. Whatever the repair job that you are doing, you need an engine to help you produce work, and this is a typical device, this is carried on the back. So you can calculate how much you can, first of all the weight of the device that a person can carry, the size of the device and all that. So there are some limitations in terms of how much a person can carry on his back and do work. But the question of thermodynamic interest is, if it works under sea water for example, this is at temperature T which is fixed, both are at temperature T, it is isothermal operation effectively, because the temperature of the water outside will determine the temperature of the whole process. So under isothermal operation, what is the total work that is done? Of course there are two ways of calculating it, and this is the trouble about thermodynamics. One way turns out to be trivial, the other way turns out to be somewhat complex, but the answers are the same, they have to be the same in any case. So for example, if I want to calculate the work, I can take the engine alone, I can do it as an open system where I define contents of the engine. That is my system. So I have gas coming in, gas going out, and I can ask what is the work done. We derived an expression for the work done. If you remember, this expression had delta Ws was less than or equal to, it was in isothermal operation, it was G out minus of G out Tm out minus G in Dm in. I think minus you had this du nt ds, of which at steady state we said du and ds are 0, but apart from steady state, if you have a system like this where the total amount of gas flowing through the system over a finite period of time of interest, I mean do not make that time too short, the total mass flowing through is much larger than the hold up in the system, then this du represents change in internal energy of the contents of this device, and this contents is not at steady state because this pressure is falling, this pressure is rising. So the pressure will change, so the contents will change, but the mass inside is negligibly small, therefore the internal energy is negligibly small, the change in internal energy is even smaller. Therefore we throw these two terms out, in this case not because of steady state but under conditions of negligible hold up. If you try to analyze the system for a microsecond or something, you will get wrong answers because then this assumption is not valid, but you are normally worried about finite periods of time during which the amount of gas passing through the system is much larger than the negligible, I mean negligible compared to the mass passing through the system during the period of interest. So if I have gas passing through this and under negligible hold ups, then dm out is equal to dmn because the mass inside is negligible. So you simply get delta Ws by dm is equal to delta G. If you are trying to calculate the maximum amount of work, you are talking about P1 is equal to P0 initially, P2 equal to 0 or near 0, P1 final, this is initial, final should be equal to P2 final. Till the pressures are different, there will be work that you can extract. In this case I am talking about isothermal operation, which is why I got this result delta G here. So if I want to calculate Ws, simply integral of delta Ws over the entire thing is equal to integral of minus delta G times dm from the initial conditions to the final condition. On this diagram, what is plotted are constant specific volume lines. So instead of the m there, mass is simply equal to volume by the specific volume. In the volume of the in this case, for example, you can take the mass here, you can integrate over this condition here, and the mass here will be simply the total volume of cylinder 2 divided by the specific volume in cylinder 2. Okay, this is actually the hard way. I will do this calculation a little, I will do this in a minute, but the easier way is to take the closed system. In fact, as a thumb rule, as far as possible, define a closed system which will still give you the answers that you need. In this case it is tank 1 plus contents of engine plus tank 2. I take all of them together, or contents of tank 1 plus engine plus tank 2, contents is outside. This is a closed system, no mass change in the system. If it is a closed system, you know that delta W is less than or equal to minus delta A under isothermal conditions. So all I need to know is A final, W is simply equal to A final minus A initial with a minus sign. And this is also easy to write down because this is MF. Remember, in the final state the pressure is the same in both, so I can take the total mass MF into AF. It is a homogeneous, it should be a minus sign here because I take the minus inside, plus M initial in tank 1 times A initial in tank 1 plus M initial in tank 2, A initial in tank 2. When I derive a result for closed systems, the system does not have to be homogeneous, it can consist of several homogeneous parts. You have to add all the thermodynamic properties. So AI is actually A in this tank plus A in this tank, the engine mass negligible, I mean the mass, the contents of the engine are negligible. In this particular case I have taken initial mass as 0 here, so I can strike this out, negligible mass initially, I evacuate this cylinder. So I have simply MFAF plus, in this case these two are equal, M is simply MF is equal to MI in 1 tank 1 is equal to V of tank 1 by V initial in tank 1. So I must give you the size of the two cylinders. Capital V is the total volume of tank 1 V1, capital V2 will be the volume of tank 2. To calculate Vi, I know the temperature and I know the pressure initially P0. So we will take some numbers here, for example if you take let us take some numbers from here. For example, I will take example, I am taking methane only because I have a chart on methane. Nobody will be foolish enough to run this with methane. I mean the best way to run such an engine is with air. So if air leaks, you do not have to worry about destroying the ecology in the fish and all that stuff. But just for example, let me take some reasonable temperatures. So let me take 10 MPa. Let me say I filled up to 10 MPa. I can take a temperature, I do not think I have a choice here, this is sea water. So we will take something like 20 degrees C. Degrees C would be about 270 73, let me take 300 degrees K for convenience, that line is here. So you can read the 300 degree K line here. So 300 degrees K and 10, what I need is simply A at these conditions. This is the initial condition. So what is A equal to? A is H, you need to get several variables because it is H minus PV minus Ts, right. I have H, PV, T and S, all these are available on the chart. So T is known, you have to read S on the table in the, so you just take the intersection of 300 degree K line, which is an isotherm, you can see that line there, it comes down and meets the 10 MPa line at something like 550 enthalpy roughly. My eyes are far worse than yours, so you can read some numbers out. Will you tell me the numbers? This is about 550 for example, in whatever units, this is kilojoules per kilogram. The pressure of course is 10. Can you tell me what V is at that point? You just identify the intersection point and then read everything from the graph. This is great fun, somebody else draws this graph for you and you just read numbers from it. So the whole calculation is trivial. What is your V? The V lines I pointed out to you that V is the slope of the V lines, you remember we got the slope of the V and the S lines, actually these are marked here. So the S lines have a steeper slope, the flatter lines on the right hand side are the V lines, the line that passes through this about 10, these lines are lines of, he has marked density, is it? Okay, they have changed, this is not specific volume, actually density is given. This chart has changed since the last edition. So this is actually 1 by that, so this is about 1 by 10 meter cube per kg. I am reading numbers approximately, you read them more carefully, and normally the PV product is negligible compared to H. So H minus PV, H and U can be equated for most purposes, and then you have TS, S you can read here, what is the value of S that you get here? 17 is it? This one? 17? 70, sorry. Oh, it is much higher, yeah, right, okay. Then what about the entropy? Is it 9? It is 15, 20, it is higher I say. It 30, 50 and 70, it is almost 70. No, it is not, sorry, I take it back. I am allowed to make mistakes, you are not. One of my problems is that it is about 10, yeah you are right, about 10?
7,
9, okay. And this is of course 300. So that is your initial value, and you have to know the volume as well, I mean the mass. The mass is simply the total volume. What do you think you can carry on your back? What kind of volumes can you carry? 1 meter cube will be too big. So let us say the larger one will be about 0.1 meter cube, this is about 0.01 meter cube. I am just giving you some numbers. This will be strapped on your back. So the m will be 0.01, which is meter cube, divided by or multiplied by the density. In this case he is giving you density. Actually those are constant volume lines, is the same as constant density lines, they have marked the density on it, that is all. 0 1 into the density is, we just saw 1 by 70, no 70 kg per meter cube. So you will multiply m into A, this is A initial, this is m initial, so you have got this figure. To get the final state, you have to realize that the total volume is given, it is an isothermal operation, so the mass is the same. So to get the mf is the same, this is also equal to mf, is equal to mf. So the final density rho f or 1 by Vf final density is simply mf, which is this divided by V1 plus V2. So it is 0.11, it is 1/11th of the initial density. So you had already 70 by 11. So you have to find the 70 by 11 curve here, and that is one fixed point. Then you are moving along the isotherm, so along the 300-degree line you locate the second coordinate is simply the volume. So 70 by 11 is what, about 6. So you see the volume line at 6, somewhere at about 6.6, it intersects the 300-degree line at some enthalpy which is about 650. So you have to locate that point, the enthalpy at that point, again you are calculating AF is equal to HF minus PFVF minus TSF. This HF is about, you can read it more carefully, 650. And the reason these numbers decrease as you go to the, as you move left, for example, as you move from vapor to liquid, is because the 0 point of energy is considered when two molecules are infinitely apart. So as they move closer, attractive forces between the molecules, work is done, if you push the one molecule towards the other, work is actually done by the system itself on you, on the second molecule. The first molecule is attracted by, the second molecule is attracted by the first molecule, so the energy will actually decrease, so it will always go less. You take the ideal gas, infinitely separated molecule as the 0 of the energy. So this is HF, this you can read PF, we have already seen what this is 11 by 70. You can read PF on that intersection again, I don't know what it comes to. You get something like 1, PF is approximately 1, then T is known, T is again 300, and finally SF. SF is about 10.5 or something, yeah 10.5. You go to lower pressures, there is higher entropy because there is greater movement of the molecules, more freedom for the molecules. So you calculate this AF, then multiply by MF, which is the same, you get a number which will tell you the maximum work you can get out of this system. What you want is actually shaft work. What you get there is W, right? How would you find the shaft work? This will give you shaft work directly, the open system analysis will give you shaft work directly, but on the other hand that is so much easier to do the calculations for. To get shaft work, all you do is go back to the definition. Ws is W, total work done, shaft work is minus total work minus the flow work. Flow work done by the system is here in the outside, minus, I will simply say flow work. I will have to do the flow work calculation because flow work calculation depends on the outlet conditions, and the outlet conditions keep changing, so I have to integrate from initial state to the final state. Normally if it was an ideal gas, for example, PV would be RT regardless of the state here, the pressure and the volume change, but PV is RT. So in an isothermal operation the work here will be the same as the work in. So for an ideal gas there will be no difference at all, flow work will be 0, Ws will be equal to W. In many cases flow work is negligible, so Ws will be approximately W, but we can calculate that exactly. I will do this other calculation, then it will become clear as to what we are talking about. Is that calculation clear? While it looks a bit messy when you first see it, you can see that once you have a chart you are empowered. So essentially you have the chart, then you can do any calculation. If somebody has done the chart for you, then all you do is locate these things in a mysterious way. If you are impressing a layman, you can always do this, move your fingers and locate a point and say point A, point B, and then calculate the differences and so on. But the calculation itself is trivial, and you can get out of thermodynamics only the maximum work that you can get from the system. In actual practice you will get less because of various frictional losses and irreversibilities. But then you can design your system better and better, and you can say if it gets to within 99% of the thermodynamic result, you say stop improving the system, it does not help you. Now let me do the second calculation, although it is quite illustrative, and finally you will be able to match the two. What I want to do is to calculate delta G into dm. This is the integral I want to calculate. This mass could be any of them because the mass leaving 1 is the same as the mass entering 2, so I can start with either one. Let me start with this m, dm is equal to dm in tank 2, because in tank 2 mass is increasing, you are looking at the flow through the system. It is also equal to minus of dm1, could use either one. Delta G is the difference in free energy between tank 1 and tank 2. So this is integral dg is equal to integral minus sdt plus vdp. Now this is just a thermodynamic property per mole, therefore it is like the closed system equations. This is 0 because it is isothermal operation. So all I have to do is to calculate integral vdp. This is from inlet to outlet, so this is from P, outlet is P2, inlet is P1. Delta G is G out minus G in, G out is the same as G in tank 2, G in is the same as G in tank 1. At this stage you have to do a numerical calculation, because in the chart you will have to start with P1 to P2 at any given mass. So when the mass is equal to m2, which will go from 0 all the way to the final total mass that was initially in the system, at every mass you have to calculate that is you assume M2, start from 0, make small increments, at every point you have to know V from P1 to P2, that is you go along the isothermal line from P1 to P2. Let me do this calculation for an ideal gas so that it is explicitly clear. So at this stage I am going to assume ideal gas. Actually you can do this for an ideal gas, you can do this analytically, because this is simply RT ln P2 by P1. I am going to integrate this over M2, so I have to relate the pressures to the mass. This is the same as RT ln P2 is rho RT, because it is ideal gas. This is equal to RT ln, the density is simply mass in tank 2 by volume of tank 2, and this is volume of tank 1 by mass in tank 1. Mass in tank 1 is M minus M2. I am not doing it for methane, I am doing it for the ideal gas right now. For methane you have to do the same thing, but you have to do it numerically by going along the isotherm. Or I can give you an equation of state, I can give you something like van der Waals equation of state to describe methane, then you will do the integration using V from the van der Waals equation of state. Now I have to do this integral over dm, dm is dm2, so I will simply get delta G, erase this, since I want to get Ws, this is equal to minus integral of delta G dm2. I get RT ln V1 by V2, which is a constant, times M2, not M2, the total integral is M2 equal to 0 to total mass into M final. Integral of this from M2 equal to 0 to M final. This is logarithm of V1 by V2 plus logarithm of the second term. So I have split it into two parts. Log of V1 by V2, this is a geometric factor, this is a constant, therefore I just integrate it over the entire mass. So I get the total mass flowing through the system, which is equal to the total mass in tank 2 at the end of the process, which is simply MF, minus RT ln, this you know how to integrate, just log x dx and log of A minus x dx. In the same case for an ideal gas, for delta A, this would have been simply equal to, again I have to integrate the same thing, dA I have got A final minus A initial, that is all. The same calculation I have to do, which gives me MF I can pull out, MF times integral dA from initial condition P0 to Pf. And at constant temperature dA is actually minus STT minus PdV, So this is simply minus or plus integral mf times p dv from p is equal to pf to p is equal to p0. I will switch the 2 for the minus sign, switch the limits. So this again is RT by V, so you get MF or delta A is equal to MF into RT ln V initial at this is RT ln V by V final. Is equal to mf into RT into ln, because the mass is the same I can multiply by the mass. Any V initial into M initial would give me simply V1, and V final into M final will give me V1 plus V2. I want you to compare this, which gives you actually W, in this which gives you Ws. Complete this integration and you will find that the two expressions are identical, because flow work in an isothermal ideal gas system is net flow work is 0, flow in is equal to flow out. If you want to do a proper a professional analysis for industry or something, they have to get the database for you. Many of them have access to database. In these cases, as far as this course is concerned, you can use trapezoidal rule for all integrations. If you are doing VDP numerical integration, you simply take V2 plus V1 by 2, under the in those conditions, and just integrate using a trapezoidal rule, that will do. Then for accuracy you can go to any level of accuracy later. Okay, I will stop there.